Very good. All right, what we're going to do is first is the July 2016 test 1 for 214. What I did notice, I went online to get another copy of this. The multiple choice solutions are already online. So what I'm going to do is I'm going to skip the multiple choice in lecture. You can look at that, and if you have any questions, come see me this afternoon, or you can ask during class if there's one in particular that is a little bit weird. So this is the test, and as you can see, there are some consistencies with yesterday's test. There is an RC circuit that's a little bit more simple. There is a charge problem, which is going to be on the test. There is a resistor REQ, I0, and VA problem, which is going to be on the test. And then this guy. So what I think is going to happen is you're going to get an RC problem, appetizer, or real problem. These two will be on the test. Not exactly, but they're cousins. And then you're going to get some type of motion or potential problem. And so we'll work through these. Now the first one is an RC circuit problem. It is a charging capacitor, and this will address the questions that some of you asked earlier. It's definitely charging because at 0 seconds the potential difference is 0, and at 40 seconds the potential difference is 80. So we're going to use the charging equation. The charging equation looks like this. Now most likely what will happen is I need to go in there into the because it was mentioned in the in these that specifically the potential charging and discharging equations weren't in there. It was just the charging and discharging. And I showed you earlier the V for charging is going to be the potential of the battery times 1 minus e to the negative t over tau. And that's charging. You know that Q is equal to CV, or that V is equal to Q over C. And what I'm doing now is I'm just showing the derivation of the equations given in the test. This becomes Q over C is equal to Q max over C, 1 minus e to the negative t over tau. C's cancel because they're the same, and you're left with what is given on the test. And so most likely what I'll do is it will be a potential difference problem, and I will just give you the potential equations. But all you really need to do is switch the Q's to V, and then you got it. I mean, there's no big change in the equation. This is definitely the charging equation because let's say, as an example, you don't have to do this on the test. I'm just identifying what's going on. You plug in the endpoints. Time will either be 0 or infinity as a test for the equation. If it is 0, this means that V is equal to V of the battery, 1 minus e to the negative 0 over tau. This gives you V battery 1 minus e to the 0. Negative 0 is still 0. That makes this VB 1 minus 1, which is VB 0. And I'm doing this in painful detail, which is 0. So at time 0, this particular equation will give the value of 0, which is what you expect for a completely uncharged capacitor. For time is equal to infinity, this becomes V equals VB 1 minus e to the negative infinity over tau. What I'm going to do is I'm going to switch this to VB, or you could use no, VB is still fine. 1 minus 1 over e to the infinity over tau. Now, infinity over tau is still infinity. So this becomes VB 1 minus 1 over e to infinity, which then 1 over e infinity is infinite. That makes it 1 minus 0. Which means that the potential difference across the capacitor at a long period of time later will give you V sub B. And so one of the things that I do is you just recognize that's a charging equation. The one without the 1 minus is the discharging equation. You could do the same thing, plug in 0 in that other one, and you get V battery. If you plug in infinity, you'll get 0 for that equation. So it's the first layer of defense is just to straight up memorize the proper identification for the equation. The second stage, if you're still confused, you just plug in the endpoint 0 and infinity and see how the equation works. Now we have a charging capacitor, so what I'm going to do is, well, I'm looking for R and tau, the resistance and the time constant. I'm looking for, the battery, which in this case I used V naught. So V naught, VB, same thing, V battery. 203 volts, which is an odd number, literally and figuratively. The capacitance is 20 microfarads, or 20 times 10 to the negative 6 farads. So what I'm going to do is follow my own advice. I'm going to change anything, if it has a milli, convert it to just the straight up units. Millifarads to farads, microfarads to farads, nanocoulombs to coulombs. Get it into that scientific notation. We have V equals V battery 1 minus e to the negative t over tau, and identify what I know and what I don't know. I know at time equals 40, the potential difference is 80. So I know what V is. I gave you the voltage of the battery, V naught, so I know what that is. I know what the time is. The time is equal to 40 seconds. So I know what time is. The only thing that I don't know is tau. And so what I'm going to do is I'm going to solve for tau. Yes?
Did you start over? Why did you switch it from Q originally?
Why did I switch it from V naught to VB?
From V to Q over C.
Oh, this is because of, like, everything right here, I blame her. Because she was asked, I'm not blaming her, she was asking about it. Because what happened is, she noticed in this particular problem, I was asking about potential difference. In the in the list of equations, I used Q. And she was wondering, how do you get to V? And I was like, well, it's just you just do a straight up change. It's not that big of a deal. But what I'm going to do is, as I've said, these test reviews are just dress rehearsals for what's going to happen on Monday. And so when I look at this, I go, yeah, I'm probably going to change that over the weekend. So now we need to get my tau extracted. So V over VB is equal to 1 minus e to the negative t over tau. That gives me e to the negative t over tau is equal to 1 minus v over vb. Oh, yeah. Okay. And what do we do now with exponentials? We attack it with a natural log. So natural log of e to the negative t over tau is natural log of 1 minus v over vb. That leaves us with negative t over tau is equal to natural log of 1 minus v over vb, or negative t over ln 1 minus v over vb is equal to tau. Now tau is measured in time, and we have a negative time in our numerator, which is a little bit upsetting. But remember, v over vb is going to give us a number less than 1. So 1 minus a number less than 1 will still give us a number less than 1. And a natural log of any number between 0 and 1 will give you a negative number. So that negative number down here will cancel out with that negative sign there. So this is negative 40 natural log 1 minus, what did I do? 80 over 203. 203 sounds like I was desperately trying to get the numbers to work. 80 divided by 203, 1 minus that, natural log of that. Ah, yeah, because you could see, because the natural log of that number is negative 0.501. So negative 40 divided by answer gives us 79.84 seconds. So I was gunning for 80 seconds, but I couldn't get it just quite right. That's the time constant, tau. The next thing to do is to determine R, and RC is equal to tau. So tau is, no, I'm not looking for that. I got that. R is tau divided by C. So this is 70. Actually, what I was really going for, tau I was going to set as 80. C was going to be 20 times 10 to the negative 6. So 4 times 10 to the 6th. Is what I was really going for. Probably what would happen is in the spreadsheet, I would sit there and go, it's 203.298. I'll really work on getting it to be so close you can just round it. And that's the appetizer. So the appetizer is something that you should just be able to just bam, bam, bam it. Problem 1, which is, problem 1 is a lot like, well, it's like the vector addition problem from test 1 in 213. It's been in every single 214 test 1 since the dawn of time. I don't think, maybe when I was teaching 212 it wasn't, but I have a charge. Oh, and you look at the numbers and you go, oh dude, I was totally copying off from another semester. Wait, is this the same problem? So charge 1, no, the charges are different. 12 microcoulombs at the position 4, -2 millimeters, and 2 is -10 microcoulombs at 2.5 millimeters. First thing you want to do is draw a grid. So this is a position grid. I am looking for the E field at coordinates -2, -2. So I want to know the E field vector at that point. Now at 4, -2, 2, 4, -2. Yeah, this is definitely slightly different. Or definitely different. There is a 12 microcoulomb charge there. Positive charges I will label in red. If this is a positive charge, the electric field radiates outward, which means at this particular point, the electric field goes in that direction. That's going to be the instant conversion vector of the two, because they both have the same y coordinate, -2. 2, 5 is 2, 5 is up here, and there is a -10 microcoulomb charge. Now looking at this, it's a negative charge, which means it radiates inward. I'm going to use blue as a negative. So the E field points in this direction, like so. Now we use, what I'm going to do is I'm going to do parallelogram method or tip to tail method. And if you draw those E fields out into the form of a parallelogram, the total E field at that particular point is going to kind of go up and to the left. Now remember what I said about vectors. Vectors are not location based. They are magnitude and direction based. Yes?
Really quick, can you just re-explain briefly how you determine what way the E field's going?
Okay. If I have a positive charge just by itself, I know that the electric field all radiates outward. So if I'm at a point here, what I do is I draw a line through that point, and it's a positive charge, so I draw the arrow away from the source charge. In the event of a negative charge, those electric field lines all go inward. So if I'm up here, I draw my negative line or my dotted line through that point, and then I draw towards it. Now what's really interesting is that this is lower to the right, this is down and to the right of the charge, and it's the E field is down and to the right. This is up and to the left, but the field is still down to the right. The important thing is positives radiate out, negatives radiate inward. Draw a line from the source charge to the point you're studying, and then if the positive charge, you draw away. If it's negative, you draw in. And that's how I determine. This effectively the line is like this. It's a positive charge, so I radiate away. This is a negative charge, so at this point I did the dotted line and then I drew inward to the charge.
Thank you.
All right, you're welcome. And if you ask that question, I know half the class has that question. So this is the biggest difference between, with straight up vector addition in 213, you're directly looking at forces that go boom, boom. With E fields, you've got to pay attention to the charge and positioning of the charge, because you're gonna have to think it through. First thing that I need to do is I need to find the magnitude of the distances. This distance here, it starts at -2. Its x-coordinate here is 4. So the total distance is 6 millimeters, or 6 times 10 to the -3 meters. I'm gonna follow my own advice, and I'm starting to convert everything into meters. The change from there to there is -2 to 5, or 7 times 10 to the -3 meters. The change in x, -2 to +2, or 4 times 10 to the -3. So whereas the distance, I'm going to label this 1 and 2. R1 is equal to 6 times 10 to the -3. R2, and I'm going to use just R2 squared, that is equal to 7 times 10 to the -3 quantity squared plus 4 times 10 to the -3 quantity squared. And that will give me oops, it helps if you input the right number from the start. That gives me a number of 6.5 times 10 to the -5, and you would get meters squared. Now R1 is this, so R1 squared is, let's see if that gives me a nice number. And to the people who are wondering why I'm keeping everything squared and not taking the square root of it, we will find out shortly. So R1 squared is 3.6 times 10 to the -5 meters squared.
I have a question.
Yes.
Where, for the 4 times 10 to the negative, I understand 7 times 10 to the negative squared, but why are you asking the 4 times 10 to the negative squared?
Because the x-coordinate here for this particle is -2. The x-coordinate here is +2. So the change in x is 4 times 10 to the -3. You're interested in the change in coordinates. Who asked the question so I could at least look it up? Okay. I'm looking for the change in coordinates, not the coordinates themselves. I use the coordinates to find the change. So if it starts at -2 and ends at 2, the change in x is 4. If y goes from -2 to 5, the change in y is 7. And so that's where you get it. Now, why am I keeping my r's as r squared? Because the electric field is kq over r squared. So the magnitude E1 is kq1 over r1 squared, and E2 is kq2 over r2 squared. K is a constant. It will be given. This is not botany. You don't have to memorize this. How did I memorize it? When you say it 50 billion times, it just hangs in there. R1 squared, 3.6 times 10 to the negative 5. It's already been squared, so I don't have to do anything with it. R2 squared is 6.5 times 10 to the negative 5. Now Q1 and Q2, it's a capital Q. One of the things that we're consistent about with dealing with electric fields is that Q1, capital Q, is always positive. There is no negative. So even for the negative sign, or the negative charge, this is 12 times 10 to the negative 6. This is 10 times 10 to the negative 6. No negative charge. We're interested in only magnitudes at this point. And I get, whoa, big whole number, 3, 6, 9. I get 3 times 10 to the 9th exact newtons per coulomb. Though intermediate units, I don't care about. 9 times 10, negative 6 divided by 6.5, negative 5. This one is a nastier number. 1.385 times 10 to the 9th. And you could say newtons per coulomb, it doesn't matter. What we have done is everything is, this is just leading up to the vector addition part, the vector addition part that we all have learned in 213. Vector E1 in component notation is trivial. This vector goes due left or due west. So it's a negative x component. It's an instant conversion vector. So this becomes negative 3 times 10 to the 9th x hat plus, and if you want to write it, it's fine, 0 y hat. E2 is a little bit tricky. Well, not tricky, it's just, it is a non-instant conversion vector. So we're going to have to reason it out. The thing that I need first from this, when you look at this blue vector right here, and that's the vector for E2. Actually, I was being nice to the class at the time. What quadrant is that blue vector? First, it goes up and to the right, which means both components are positive. I need this angle here. And because it's first, the reference angle and the absolute angle are identical. And how do I get that angle? I take a look at that length and take the inverse tan of the ratio of opposite over adjacent. So let's do that. So tan of that theta A is the delta y over that delta x, which is equal to 7 divided by 4. Now, at this particular point, I could have included, technically, I should put 10 to the negative 3 and 10 to the negative 3, but they cancel, so it doesn't matter. Theta A is inverse tan of 7/4. So 60.26. degrees. So that's the angle. Now, this vector, I know its magnitude, it's 1.385 times 10 to the 9th. I know that theta, 60.26, which means that E2y is E2 sine theta A, or 1.385 times 10 to the 9th sine 60.26. E2x is E2 cosine theta A, which gives me 1.385 times 10 to the 9th cosine 60.26. Now these are both positive. It's a first quadrant angle. Even though the point is in the third quadrant, that's a physical location. It's not the direction of the vector. The vector direction is up and to the right. So 1.385 10 to the 9th times sine of 60.6 gives me positive 1.21 times 10 to the 9th x hat. Ooh, wait, did I do? No, that's cosine. 1.21 times 10 to the 6th y hat. Now, I've got to use cosine for x. And that gives me 6.80 times 10 to the 8th x hat. Whoa, where did that, hold on. That's a 9, because that is 10 to the 9th, that is 10 to the 8th. So my final E total vector, its y component is 1.21 times 10 to the 9th y hat. Its x component is negative 2.32 times 10 to the 9th x hat. And if we're going to be nice and put all the bells and whistles on it, that is the E field vector in component notation with the units. Once we get it to this, it's all downhill from here. Once we added up the vectors, we've got what we're looking for. The parallelogram method suggested that it was going to be a second quadrant angle, or second quadrant vector, negative x, positive y. It is a second quadrant vector. So this brings us to drawing this out. The E field total vector is EX squared plus EY squared square root. So this gives us quantity negative 2.32 10 to the 9th squared plus gives us that. And my answer is 2.62 times 10 to the 9th nano, or newtons per coulomb. The last part is to find the angle. It's a second quadrant angle. So these are my magnitudes, E sub y and E sub x. That is my reference angle. The theta r is inverse tan, and just to stress how strong this is, absolute value of EY over EX. You never put negative signs when you're determining reference angles. This is inverse tan of, now it's the same thing. Both are 10 to the 9th. So I can just put in 1.21 over 2.32. And that will give me the angle. And that gives me an angle of 27.5 degrees. It's a second quadrant vector. Second quadrant vectors have angles between 90 and 180. So to get this angle, theta A, it equals 180 minus theta R, which is equal to 180 minus 27.5. And that will give us 152.5 degrees, I think, if the adding. Okay. So my final answer, 2.62 times 10 to the 9th newtons per coulomb at 152.5 degrees. And so that is an E-field vector addition problem. It is tedious. It's one of the problems. Like during, I know that's a big guy, and so it's kind of makes me motivated to make the other two problems not true appetizers, but make it a little bit on the lighter side. All right, problem 2. Problem 2 is a one-dimensional motion problem with an E field. The first thing that I want to do is I want to talk about the problem itself. I've got a negative charge initially at rest. Negative charge initially at rest. 20 seconds later, it's over here to the right. What direction is the E field in order for it to accelerate to the right? Right to left, correct. That negative charge, seeing an E field to the left, will want to accelerate to the right. It's equivalent to get an E field going to the left, you either put a positive charge on that side or a negative charge on that side. That negative charge would be repulsed and it would be attracted. So it's the E field is definitely to the left. For problems like this, I tend to use all magnitude. I was very nice. The x is 0, it's to the right, acceleration is to the right, motion is to the right, velocity is to the right. Now that I know the direction of the E field, I know that it's a one-dimensional motion problem. X equals x naught plus v naught t plus 1/2 at squared. X naught and V naught are both 0. The origin was set at the starting point. There's nothing I need to know about velocity. The other two equations that I need to know is that force, according to Newton's second law, is ma, and that force is equal to QE, which is the force on a charge in an electric field. So QE over M is equal to A. I don't have A, but I can substitute in what I need. X equals 1/2 QE over MT squared. Now what I'm going to do at this point, granted I am using a lowercase q. Q is negative, but E field is to the negative as well, so I got a negative of a negative and it cancels out. But what I've done is I've used logic to determine the direction of the E field because of the charge. So I'm not going to pay any attention to the signs of the charge anymore. All I'm interested in is the magnitude of the charge itself, and then I'm going to slap a negative sign in front of it because I know it's a negative charge. So this becomes 2mx over ET squared is equal to Q. 2 times its mass, 3 times 10 to the negative 3 kilograms. Remember to convert these into kilograms because force is newtons and newtons uses kilograms. X is 100. E is 25. T is 20. So 20 squared. And that gives me a charge magnitude of 6 times 10 to the negative 5 coulombs. So the actual charge is negative 6 times 10 to the negative 5 coulombs, or negative 60 microcoulombs. Probably what we'll do is we'll just accept coulombs as the final answer. But that's a motion problem.
I'm sorry. Since the E field is going to the left, you just put the negative charge in front.
I just put the negative charge in front. What I'm really doing is I'm saying, I know it's a negative charge. I've just figured out that the E field's going to the left. So after that, all I'm interested in, I know that all the motion is to the right, and I just dump signs out of the equation because I'm interested now in only understanding about its magnitude. Once I have its magnitude, I know it's a negative charge anyway, so then I just slap a negative sign in front of it. I'm a big fan of in certain cases like this, keeping things positive and letting logic dictate signs. Because a lot of times, and this is from my own personal experience, I get confused. Is it a negative of a negative of a negative? But is there another negative? And then I just go nuts. So that's why I tend to deal with the magnitude system. Last problem. The circuit. All resistors are 4. I want to know Req, I naught, and VA. Basically, I'm going to take test 1, the template for it, and all I'm really going to do is change the equation, change the numbers, but that sentence will remain the same. What you do first is you squoosh. The first thing I do before squooshing is I redraw it in a nice way. But wait, it's all curved into circles. I don't care. It's the same thing. Some people get freaked out. Instead of drawing this, Occasionally, I will draw that. There is no difference between this and that. Both fork, left and right, or up and down. Upper fork has 2 resistors, lower fork has 1 resistor. It's the same thing. What I traditionally do is I look at this and go, he was trying to confuse me. And then I redraw it like this. And then to me it looks a lot more simple, or looks simpler. So I do my squooshing. There are 2 squooshings I can start with. One where 2 of the resistors are in series. All of the resistors are, I'm going to use R. So I simplify it to that. The next squooshing are 2 parallel resistors, which gives me that. And then the last squooshing will give me REQ. And so that's the procedure, just drawing it out. Now let's go get some numbers to this. All of the resistors are 4. So this is 4 for certain. That just goes down to there. That's 4 because that goes down to there. Those are 2 resistors in series, so that becomes 8. These are 3 resistors in parallel, so it becomes 1 over 4 plus 1 over 4 plus 1 over 4 inverted, which becomes 4/3. 1/4 times 3 is 3/4. Invert it, you get 4/3. So that makes this 4/3. That comes down, that doesn't do any changing. Remember, I'm using fractions. Do not use decimal until you give final answers. 4 becomes 4. And then this resistor, 1 over 8 plus 1 over 4. This is 1/8 plus 2/8, or 3/8, or 8/3. Now you just add them up. 4 plus 8/3 plus 4/3. 8/3 plus 4/3 is 12/3. 12/3 is 4. 4 plus 4 is 8. So the equivalent resistance of the whole thing is 8 ohms. That's the first step. Next step is trivial. I naught, Ohm's law, V over REQ. V is 2, REQ is 8, I naught is 0.25 amps. The grader will be told to headhunt for units. If you say the current is in terms of ohms, don't do that. Just don't. Just don't. If you say the potential difference is 8 amps, I'm gonna freak. I can tell when you're doing it in the test. Now the next part is to find the potential right there. So how do we go about doing this? What I would do is I need a lot of things. I need the potential here, which I will call VB, and I definitely need the potential here, VC. the quickest way to do this is to get VB, I'm gonna step down from the battery, which is 2 volts. And to get VC, I'm going to step up from down here, which is 0 volts. Because on one side, we're at the positive end of the battery. On the other end, we're at the negative end, or the ground. To get VB, it is V high minus I naught R, the resistor that we're passing through. To get VC, it's V low plus I naught. And then what I'm gonna do is I'm gonna go use R, what subscript am I gonna use? R sub C, and R sub C is this guy. R sub C is those 3 resistors in parallel. I'm gonna treat it as one resistor. This is why I keep track of all my intermediate resistances, because it just makes things faster. V low is 0, so that goes away. V high is 2 minus 1/4 times 4, so V high is 1 volt, or V sub B is 1 volt. VC is I naught 1/4, RC, which is 4/3. So VC is 1/3 volt. So now I have VB and VC, and I used an intermediate resistance in order to get to the point. Yes?
Where did you get those equations to find VB?
Everything that I do is based on, and technically, yes, I skipped a few steps, but really what I'm doing is I got this equation in my head, and that is I equals V high minus V low over R. Here, VB is V low. So IR V high minus V low, or V low is equal to V high minus IR. Here, VC is V high. So V high is IR plus V low. So they're just variants of they're variants of Ohm's law. And so yes, I just slapped it together in my head. You asked how I got it, so I should have written that out first. But that's what you need to do. So I've got VB and I got VC. VA is sitting in the middle of this. I know VB 1 volt, VC 1/3 volt. Really what I'm going to do now is I'm going to combine the two effectively, 8 volts with a VB of 1 and a VC of 1/3. This means that I can get the current passing through those 8 volts. I know the total resistance, I know the high, I know the low. The only unknown is current, which is for this. So this becomes 1 minus 1/3 over 8, or 2/3 over 8, or 1/12? 1/12? Yeah.
You got that 8 from 2 plus 3?
No, I got it from the fact that those two resistors are each 4. So 4 plus 4 is 8. So this is 1/12 of an amp. Now that I know the current flowing through, I know the high of 1 volt. I know the current going through it, 1/12 of an amp. I know the resistance 4. So what I'm going to do is I'm going to step down from VB to VA. So this is, I'm looking for V low, so I'm going to use that. So V low is V high minus IR. V high is 1 volt, I is 1/12, R is 4. 1 minus 1/3 or 2/3 volt. And that's how you get it. This is kind of a Sudoku puzzle type problem. I'm not going to go into super complex circuits for this. I mean, this will be as complex as it gets for the test. The only way really to understand it, where's the... Where are my problem stuff? There you go. This is why I was such a jerk on these 3 problems. Having you go through and step through it over and over and over again to give you guys practice. To help develop your sense in how am I going to figure out this potential at this resistor? Well, I kind of need to know everything about a particular point. It may not be the answer I'm looking for at the end, but it's a sub-problem to get me to that point eventually. And so that is that. In terms of practical parts of the test, test 1 starts at 10, ends at noon. We're going to go for the 2 full hours. We're not going to have any lecture in the second half. So you can use the whole time. You can use probably, I'm going to write a test so that people really should start walking out the really good ones at about 50, 55 minutes. And then the bulk of everybody leaves at about hour 15, so about 11:15. And then there'll be people that I'm going to have to pry the test out of their hands at noon. So it's going to happen. And then we don't have any lab that afternoon. So then you can go play in the yard, do something. I don't know. And then just to set up what's going to happen next week, we're going to do the lather, rinse, repeat thing again. On the morning of the 11th, that for day after the test, I will go over Kirchhoff's laws so that you will be fully prepared for that lab that afternoon. And to let you know, I'm the Kirchhoff law master. I know the best. I look in the mirror and I say, who's the one that knows the best? Mirror says, you are. That's what it does. So trust me, I've been working on Kirchhoff's law for years, and it's something that I really know and I'm very passionate about. Yes?
So that test you only had resistors. Do we need to be on the lookout for capacitors?
I don't think, remember on the yesterday's test that we did, there was an equivalent capacitance circuit. I think that we're not going to do that. And how strongly do I feel about that? I feel pretty strongly about that. and which means that the only thing that's going to come up for equivalent capacitances are going to show up in the multiple choice. Yes.
On the appetizer, you know, I think we're given like 2 times and then 1 times a 0.
Yeah, that was really just to illustrate the point that it's charging. I was really I mean, I did say it's a charging capacitor, but I really wanted to make it obvious that at times 0 voltage was to 0. So, a lot of times people misinterpret my desire to make things crystal clear, and they tend to mistake it with I'm trying to trick people. But it's that obvious. It's just letting you know it's charging. Yes.
Okay, so you said that other problem would be potential in motion. What would be an example of the potential?
The thing, I've been thinking about that. With, it's going to be one of 2 types of problems. Either A, you're going to have a capacitor and a charge moving across, or it's going to be one of those, like, you have an object either heading towards this or away from it, and it has that distance d when it comes to a stop. And then I'm going to ask you questions about that. What we're going to do is we're going to go through both examples right now. Potential problem. You have a charge here. Initial velocity is 0. It's positive plate, negative plate. You let it go, and it moves across, and remember, this is dynamically done, so I have no. Let's figure this out. The velocity there is 300 meters per second. The distance is 0.2 meters. What I want to know is if the charge is 2 millicoulomb and the mass is 2 times 10 to the negative 4 kilograms. What I want to know is what is the E field magnitude? And what I want to know is what is the what is V, the potential difference between the plates. So for something like this, it starts at a high potential, it ends up at a low potential, it has no kinetic energy at the beginning, it has significant kinetic energy at the end. So its potential energy is equal to the kinetic energy because there is no friction. So we have conservation of energy. So E1 is equal to E2. And we got something like this. The potential energy can be described as equal either QV, or potential difference. You could say QdV or Q delta V. Either one is fine. And then V is ED. So we could solve for, let's solve for V. QV. Oh, I don't want to do that right now because I'm going to show you why. Potential energy I'm going to write as QED. Kinetic energy is 1/2 mv squared. The reason why I'm going to look for E field first and then solve for potential difference rather than solving for potential difference first is that I don't want to get confused between the potential difference, big V, and the velocity, little v. So I'm gonna stay away from that. So I have everything. So E is equal to 1/2 mv squared over QD. And when looking at all these problems, I sit there and go, well, these are kind of on the easy side. But I'm recognizing the fact that the two big problems I really believe in is the vector addition problem and the circuit problem. To a lesser extent, the RC circuit problem. So with the big, most of my energy that I think most of the energy that you're going to put into the test on Monday is going to go into E-field addition and circuit analysis. So what I'm going to do is, obviously the appetizer is going to be a little bit more lightweight, and then whatever I pick for the other one is going to be lightweight as well. Sort of like this. So this becomes 0.5 2 times 10 to the negative 4, 300 squared over 2 times 10 to the negative 3. For those of you who have never taken my course before, I'm a huge fan of stuff canceling out. 2 cancels with that 2. 0.5 negative 4 times 300 squared divided by 2 negative 3. And I get 2250 newtons per coulomb, and by some miracle it's exact. Dynamically created problems tend to be rough. This one came out with a good number, which is lucky. The last part, find V. V is equal to ED. So this is 2250 times 0.2. So 2250 times 0.2, potential difference of 450 volts. Once again, E field newtons per coulomb, potential difference, potential volts. Know the difference. And so for this, the way that I did things was mainly because the E field was continuous. For something like this, let's say we had a charge Q, which was positive 0.4 coulombs. And at a very far distance, very far, I have that same particle, 2 times 10 to the negative 4 kilograms, and the charge of that particle is positive 2 millicoulombs. And that thing was flung at a particular velocity v, and I'm looking for that velocity v. The only thing that I have to give you, in addition to everything that I've done before, is it stops. The velocity at this point is 0 meters per second, and that distance right there is 0.1 meters. I've hurled a positive charge at a positive charge, which means that there is a force repulsing that positive particle. Which means that at a very far distance, as it's approaching, it's slowing down more and more until eventually it hits 0. It's the same type of problem. It's a potential energy, kinetic energy, conservation of energy problem. Energy is conserved because there is no friction. Yay, no friction. I need to figure out how to put friction into a problem, but that's not, it's too late. I'm not going to do it. The initial energy is all kinetic. This thing is moving. It's no potential, because potential for that charge there is KQ over R. At a very far distance, R, and when I say R is very far, or it's a very far away particle, That just assumes that R is darn near infinite. So over here, that potential is 0. Over here, that potential is KQ over R. Now initially, it is all kinetic energy. At the end, it is all potential energy. The kinetic energy is 1/2 mv squared. Since I don't want to confuse big V potential difference with little v, what I'm going to do over here is potential energy is Q big V. Now that big V is the potential due to that big charge over here. So that is the, I'm going to rewrite this. K big Q. So this is K big Q over R. So potential energy is equal to Q K big Q over R. So that little charge is has a specific potential at this point here, and that is distance R, or 0.1 meters. So this becomes KQ big Q over R. Now I'm looking for the velocity. V squared equals 2Q K big Q over RM. 2 comes up, M comes down, KQQ over R, blah, blah, blah. I get this. So V is equal to square root of 2Q K big Q over RM. Two millicoulombs. K is 9 times 10 to the 9th. Big Q is 0.4. R is 0.1. Mass is 2 times 10 to the negative 4. Now this is a dynamically created problem, so I have no idea what number we're going to get. If the number, trust me, when I start writing the test, I'm gonna make the numbers legit. In the old days, you know that Bernoulli's equation problem where you got to find the velocity at the bottom of the hill, blah blah blah. The problem that I had set up, I accidentally made the answer, the velocity at the bottom of the hill was roughly 2/3 the speed of light for the fluid. And that caused some confusion amongst the students. And I said, well, just give me the number. This is an engineering problem. It's not my problem with what's going on in that pipe. 2 times 10 to the negative 3, 9 times 10 to the negative 9, times 0.4 divided by 0.1 times 2 times 10 to the negative 4. And I get, okay, it's not totally relativistic. It's 8.5 times 10 to the 5th meters per second. So it's traveling at roughly 0.3% of light speed, which is okay, fine. But that's how you would do it in both cases. Yes?
Did you, so for this one, how you equaled kinetic energy to potential energy,
Mm-hmm.
did you know to do that? It's because the ball is moving from right to left on this one.
Yeah, also the fact that there's no friction.
Is it any different than equaling like potential energy to kinetic?
Well, the problem with the big difference between these two is that the potential difference over here is E times D. The potential at any point is KQ over R. So there's a little bit of a difference. The other thing about this is here I can figure out E field and V. Over here, it gets a little bit more difficult to find the E field, and the E field is kind of unnecessary for that problem specifically. When I look at these problems, it's effectively like this. So if I throw an object up in the air or I throw an object up in the air, it rises 25 feet before coming to a stop. What was the initial velocity? That's a classic 213 problem. Now, the potential energy is not based on the height, mgh. The potential energy is based on little q times big V. And that big V in this case is kq over r. Over here, it's a little bit nicer in the sense that the potential difference is nice. The E field, I mean, it's linearly changing. It's a different type of problem. But at the core, it's still the same thing. I drop something, it hits the bottom at 300 meters per second. What is gravity is what I'm kind of looking for in a way. And so that's kind of it. Does that answer? Okay.
So is it only KQ over R squared when you're finding the E field?
E field, KQ over R squared. Now, had I asked for what's the E field at that, I mean, I guess this one right here, I would say that's an appetizer problem. To make it a real problem, I would say, well, what's the E field at that particular point? And then you would just go E equals K Q over R squared. Calculate that and then give me that. And then I would go, okay, fine, give it to me as, I could be a jerk and say, well, what's the E field as a polar vector? And so you would calculate that, and then you would say, well, theta is 0 degrees. Because you're at that point, draw the dotted line, radiate outward. That's a pure do right vector. I don't think I would ask that because on the test, you just got done doing that. And I think it's kind of a waste of time to ask the same, effectively a part of the same problem again. Okay. So anything else? Otherwise, I'll take a stab in the homework. Let's take a look. All right. In terms of let's talk briefly about problem set 3 in terms of this. Like I said, I want you guys can get in the homework by Monday morning. It's not like you're going to get this back on Monday and have it worth anything. These were done in class. This is, well, all of these were really done in tutorial. But in terms of just go through the tutorial once, get that problem solved, and then leave it alone and don't really study for it for the test. I would say that this and that for the test, the derivations, are really good knowledge to know for the multiple choice. Number 5, just play with it. I definitely won't ask for it on the test. 6 is good, 7 is good, and then the rest are kind of good. The things to know. For 12, what happens, effectively at full charge, a capacitor kind of looks like a resistor of infinite resistance. And a resistor of infinite resistance, you can effectively just remove that strand out of the circuit. So effectively what I'm looking for is just something that looks like this. And so you can do that. It's me trying to be a little bit sneaky. You're not going to get something like that on the test. 13 is me testing your knowledge of ideal voltmeter. R2 would be infinite. So effectively it would look like, well, effectively what would happen is that it would look like that. Because if you remove that section and that section's gone, R4 becomes irrelevant. Ideal ammeter, it becomes like that, because the effective resistance of an ideal ammeter is 0. So, real quick, ideal voltmeter resistance is what? Infinite. Ideal ammeter resistance is what? 0. Typical resistance of a non-ideal ammeter? Low. Like 10, 20, 30, something like that. Could a non-ideal ammeter have a resistance of 2 mega ohms? Yeah, but it would be really sucky as an ammeter. What's the typical resistance of a non-ideal voltmeter? Like 10 mega ohms. Non-ideal voltmeters could have resistances of 10, 20, 30 ohms, but they would be really sucky. So when I say typical resistance of a non-ideal voltmeter, I mean typical resistances of a voltmeter that doesn't suck. So know those differences. There were some people who said, yeah, a voltmeter could have 10 ohm resistors. And I'd be like, but it'd be a horrible voltmeter. Just horrible. Why use it? So know that. There we go. Let's see. Let's take a look at problems. Problem set 2, I would look at the test. I would look at 1, 2, 5. And you know, some jerk said that I was cruel to animals because I wrote this problem. I'm asking you to save puppies, not kill them. Cruel people. I should read. One of the things I'm going to do, well, since it's my last semester here, I'm going to do it. I'm going to post on YouTube and I'm going to read aloud the worst review I ever got. She hated me. He, I don't know. But that person despised me and just let the hate flow. And what I'm going to do is I'm going to read it and I'm going to respond to it during the reading. So I got to get it out because it's just something that I had it up on my wall for a while. It was profound hate. And then 6, kind of. So I would say 1, 2, 5, and 6 are kind of the ones that we're looking at for problem set 2. Problem set 1 could be 6, not 7. Could be 8, but I'd weaken it. And really what I'm looking at are, you know you're going to get the E-field vector addition. You know you're going to get the circuit. What I'm really looking at now are what could the other 2 problems be? Oh, RC circuits. So I'd really say nothing on that. So for the non-RC circuit problem, I would say problem set 1, 6, and 8. Problem set 2, 1, 2, 5, and 6. For the RC circuit problem, I would look at, I need a different symbol. Problem 6, We're not going to do equivalent capacitances yet. Probably that one and 9, and just understand how 10 works is, I would say those would be it. And then I think that's it. I think that's it for this. And so that's what I think is about it. I will say this. I made this problem. I'm very proud of this problem. Problems that aren't typically, that I really like, if they're not on the test, I put them on the final. So I would definitely keep your eye on that one. If this is going to be the last final that I ever give, I know I'm sad too, but I'm going to bring out my favorite hits and just give a test that I want to give. It won't hurt you. God, why the sad face? No, but it's going to be something that I'm going to leave my mark. People will go, whoa, he went out hard. And so that's it. Are there any questions? Anything left? All right. We're 20 minutes early, so you guys should appreciate. We do have lab today. No, we don't have lab because I know Daniel's not leaving. So, go play in the Grove. I don't care. Get out of here.